بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم. Last time we discussed about different way of derivation of Jacobian matrix and its mapping in force and torque relation or wrench relation. We call it static. Today we would like talk about the very most important characteristic of Jacobian matrix. As we saw, the Jacobian matrix is a matrix that maps the joint velocity space q dot into the task velocity space x dot or g dot, a tuple of 6 degree of freedom here usually, which we call it twist as well. In terms of the Jacobian characteristic, we would like to consider the inverse map. If q dot is given, certainly x dot will be found. This means that if we have the velocity of the joint angles, then we have certainly we can find by the Jacobian the velocity of the task space. But the inverse problem comes into the inverse of the matrix. And this might happen, it might have multiple solution or have no solution, like the inverse kinematic that we have. When the Jacobian is squared, if we have the same degree of freedom of the actuator, if the degree of freedom of the joint space or the number of actuator that we are considering is the same as the number of task space. So we have the same number of actuator as we require in the task. Then the Jacobian matrix, because since these two have the same dimension, Jacobian is a square matrix. In many cases we have a square matrix. We will discuss about non-square matrix in next session, but in this session we focus on the mostly on the square matrix. If it is square, the inverse Jacobian would be the inverse of a matrix, as simple as that. If it is not square, it is a bit more complicated. We call it a pseudo-inverse. We discuss it in next session. Now, consider for the square matrix, we have the inverse of the Jacobian, and the inverse of the Jacobian represent q dot, give the q dot, if we would like to have a desired velocity in the space, we would like to have a certain position velocity, angular and translational velocity for the end effector. How should we provide that with the actuator joint angles? We usually provide the joint angle to get that, and this relation provides you this demand. If you would like to have some certain velocities, then you have to provide that with the actuator velocity or the q's. So if x dot is desired and given, then q dot will be found by Jacobian inverse. And Jacobian, of course, is configuration dependent. In different configuration, it has different values. So this inverse might exist or might not exist. If this inverse exists, then we have this solution. If this inverse does not exist, if we have a square matrix that do not have a square, this will happen when the determinant of this matrix is equal to 0. Now we are talking about some properties, linear algebra properties of this matrix. If the determinant is equal to 0, then this inverse does not exist. We call that a singular configuration or a singular point. نقطه تکین یا پوز تکین یا حالت تکین برای سیستم. The singular configuration Basically, the determinant, if the determinant is 0, the Jacobian inverse becomes infinity, very, very large. Doesn't have any real value for that. This means that very little, if we have a very large number here, very little q dot will result in very large x dot. With finite joint speed at arbitrary task velocity are not achievable. We cannot have that velocity quite well. So there is twofold to represent that, to find the physical property of that. First of all, if the determinant, if the inverse is not available, so we cannot get a certain velocity in the task space. If determinant is not possible, if not defined and it does not exist, so for that particular case, at that particular configuration Q, we don't have a solution for Q dot to solve that. We cannot provide any joint motion to do that. Or if we talk it mathematically, we need a very large velocities here at Q dot at the task space to find that. And when it will happen, this is also very important. When this will happen, we can see that at the boundary of the workspace this will happen. And this is a very, very good close collaboration we have from the previous chapter to this chapter. In previous chapter, we see that the boundary of the workspace can be found where the inverse kinematic problem, which was also the inverse problem as we have in here, has usually it has multiple solution. When the multiple solution goes to each other and we have a double solution, then at that point we have the boundary of the workspace. At the very same point, we have determinant of the Jacobian equal to 0, or a singular configuration. Let's see, as an example, how this works and discuss about it a bit in more detail. Consider a very simple 2-arm manipulator, as we see in here. We have two joint space Q dot is equal to theta dot 1 and theta dot 2. We have two task space variable, x and e of the end effector, which we call it xe dot, and ye dot, the velocity of that. We have found the Jacobian in two frames. Jacobian in frame 0 was a bit involved. It has sign of theta 1 and theta 1 plus 2 inside it. If we find the same Jacobian in the task space in the frame 2, اگر جاکوبیان رو توی فریم 2 استفاده کنیم، sorry for that. If we have the Jacobian in frame 2, if we find the Jacobian in frame 2, the Jacobian is very simple, and we saw that although these two are very different, apparently, the inherent problem, the inherent characteristic of the Jacobian, like the determinant, as you see in here, the determinant of Jacobian represented in frame 0 or in frame 2 is not different. The inherent properties are the same. And we can see that it is L1, L2, and S2. And when this determinant will be 0, and when the Jacobian has no inverse, and when we are in the singular configuration, when S2 is equal to 0, and S2 is equal to 0, when theta 2 is equal to 0 or pi. And this was very, very familiar configuration. If theta 2 is equal to 0, we have fully extended arm. And in fully extended arm, we get the boundary of the workspace. And at that point, we are saying singular. And fully folded or retracted arm is when theta 2 is equal to pi. And that is also the inner bound of the workspace. At the same, both of these cases, we have double solution for inverse kinematic problem. So this relation always exists. And this collaboration that we have between differential kinematic and inverse kinematic can reveal very important text. But the important thing is Jacobian is a matrix. And we can work with that quite easily. It is much more effective to work on the matrix and on the inverse of the matrix rather than finding double solution of a for inverse kinematic map, which was quite extensively computational extensive. So Jacobian is very important, as you see here. Now, let's examine what is the meaning of that as an example. What happened at the singular configuration? To find that, we write the map, the inverse map. We know that the x dot multiplied by j dot will give you the q dot. As we saw in here, we know that x dot is equal to Jacobian times q dot, and q dot is inverse Jacobian times x dot. So we rewrite this for this general in case, since we have the Jacobian in here. If we use the general formulation in zero frame, we can find the inverse quite easily because it is a 2 by 2 matrix. We have the determinant and then just changing the map and minus using the minus sign in here. We have the inverse Jacobian, and we can find this solution for any configuration for any theta 1 and theta 2. Now, consider just a simple case that you are using x dot 1 is equal to 1, so we can have this formulation for any direction. We can move here, here, and there, but just use one simple direction, then that we are just moving it toward this line here. When x dot e is equal to 1, we are in this direction, and y dot e is equal to 0. We are not moving that one. We are just moving this way. We are outreaching toward the boundaries. We are within the boundary of the workspace. We are within the workspace, and we are reaching toward the boundary of the workspace in here. Now, if we consider this two simple one, x dot 1 e is equal to 1 and y dot e is equal to 0, this formulation will be very simple, and then we can find theta dot 1 equal to this value, theta dot 2 equal to this value, because this is 0, this doesn't come into the picture, and only this 2 comes into the picture, as you see. And if you have these two in the picture now, x dot 1 is equal to this, and theta dot 1 is equal to this, and theta dot 2 is equal to that. Now, move the system from the inside of the boundary toward the singular point, toward the boundary of the workspace. As you go toward the boundary, this theta 2 becomes smaller and smaller and smaller. And sine of theta 2 becomes smaller and smaller and smaller. This means that theta dot 1 and theta dot 2, both of them are getting larger and larger and larger. When you are within the workspace, you have limited velocity. You require limited velocity at the joints to move, to have motion. But when you go toward the end, you see that at the end, when you approach to S2 is tending to 0, then theta dot 1 and theta dot 2, both of them are going to infinity. This means that at the boundary of the workspace, when S2 is equal to 0, then we cannot have the theta dot 1 and theta dot 2 becomes infinity. We cannot reach that. This means that we cannot move forward than the boundary of the end effector of the workspace. So the boundary of the workspace is the limited point. Why it is the limited point? We cannot have motion there because there we don't have. We need very, very large velocity, infinity velocity there, and then we cannot reach that by any actuators. This is basically very, very similar to this picture. As you see, this toy is a bit farther than the reachable workspace of this kid. And although it has extended the arm, his or her arm fully extended, it cannot reach that point because this is you need velocities, infinity velocity to do that, and this is not possible to gain. So this provides us very, very interesting point. Let me ask you some questions here. You have certainly saw that and experienced that when you want to open a curtain from the wall, your arms becomes much more tense, and it is very difficult to do that. But when you do this curtain, if the curtain is not up the wall, up the wall, we are going to be very similar, singular to the singular point. Singular point, fully extended. You remember, fully extended or fully retracted. But if you work with your hand in your workspace, this is not a big problem. The singular space or singular configuration, working at the singular configuration is difficult to reach. Now let's see if this is the bad point. But singular configuration are not always very bad. They are always sometimes even very good. And you see that in this picture. Let me explain that again. The physical properties and mathematical properties of the Jacobian quadriad. If you have any question, please raise your hand. I don't want to talk too fast in here because we are discussing very important issues here. Okay, as we see in general formulation of the Jacobian consists of a number of columns multiplied by q dot, you can get x dot. These columns were J1, J2, or Jn in a simple or conventional notation, or the old previous same screw axes or screw coordinates that we had S1 or $1, $2, $n in screw base. Now we can see as a matrix or the singular value or becoming a matrix becomes singular when these columns are becoming dependent to each other. When these columns are independent, so this matrix is invertible. But if one or number of these columns becomes dependent to each other, then the singular value becomes, the determinant becomes 0 and the Jacobian becomes invertible. به فارسی توضیح میدم چون مهمه. ما ژاکوبیانمون از تعدادی ستون تشکیل شده که این ستون ها همون J1 to Jn هستن اگر از کانونشنال متد یا از روش معمول استفاده کنیم یا از اسکروها استفاده کنیم. و موقعی دترمینان ما معکوس پذیر نخواهد بود، موقعی ماتریس ما معکوس پذیر نخواهد بود یا دترمینانش مساوی با صفر میشه که این ماتریس ژاکوبیان که از این ستون ها تشکیل شده، ستون هاش از استقلال خطی در بیان و به هم وابسته بشن، یک یا چند ستون به هم وابسته بشن. حالا میخوایم ببینیم این چه خصوصیتی برای ما ایجاد میکنه. Now, if we consider a 6 by n matrix to have a general configuration, we can see that robotic n defector can reach any arbitrary twist if the rank of Jacobian is equal to 6. We can have any x dot, this still it has inverse, by q dot, by any limited q dot, we can reach to any x dot. This means that we can go toward this space in any direction, since we have the velocity in a direction, angular and linear velocity, both of them, any direction and any orientation, by a limited value of q dot, if the rank of jq is equal to 6, or the rank is the number of independent column of this matrix. So if we have 6 independent ji or screws, then we have the determinant is not equal to 0 and we have inverse. And we remember that the screw axes have some physical property and geometrical property, has some direction. You can plot them on the robot, the direction s hat and s0 hat, the distance between this direction to the 0 axis. Okay. Now, for a 6-degree of freedom robot, if the rank of Jacobian could be either 6 or less than 6, maybe in some configuration we are rank deficient, we are not invertible. If the rank is less than 6 at any point in the space, if the rank is smaller than 6, this we call that a singularity configuration, or singularity happens. For example, for a 2-degree of freedom, the same thing can happen if the rank could be smaller than 2, like the previous example that we had, and if this is if the rank becomes smaller than 2, then we have the singularity configuration. Now, what happened at the singular configuration? We discussed in the previous slide that certain direction of motion is unattainable. The kit cannot reach its play because at that direction cannot move. We have a singularity configuration at the boundary. Or defining it in any other way, bounded end effector velocities. We need some bounded end effector velocity. We would like to have a bit motion in forward in the space, but it results in unbounded joint space. So we cannot reach that because we cannot provide unbounded joint space. And these are undesired. The kit cannot play with its territory. But if we consider it the other way around, you remember that the Jacobian was also a map between the forces and the wrench, as we discussed it last session. And the Jacobian transpose was some inverse map from the task space twist to the joint space twist. Let me go back here, if you don't remember, to remind you that the Jacobian transpose was with this relation. If we have the task space, we could find the joint space quite easily. And Jacobian inverse and Jacobian transpose inverse are at the same direction. You know that any Jacobian and its transpose becomes singular at one single point. Doesn't matter if it is Jacobian or Jacobian transpose. And this means that, but you know that the Jacobian transpose means in the fourth space. So this is very good. This will give us very good solution. And as you see here, bounded joint torques result in unbounded end effected forces. What does it mean? It means that if you want to take very heavy load, like what this man is doing it here, if you want to have very heavy load, usually you fully extend your arm and then take the load up. You never do it like this way, that your arms are not fully extended, because it becomes, you need a lot of torque in your arm. But when you want to take something very heavy, it is better to become on this singular configuration, just fully extended or fully folded. If you would like to carry on a very heavy bag on your shoulder, you just put it on fully retracted configuration. As you see here again, I talk it in Farsi. اینجا در واقع چون نیروها رو ما داریم جابجا میکنیم، جاکوبیان ترانسپوز توی تأثیر قرار میگیره و ما برای اینکه بتونیم بارهای خیلی سنگین، نیروهای خیلی زیادی رو بالا ببریم، جابجا کنیم، میایم تو کانفیگوریشن سینگولار قرار میگیریم. تو کانفیگوریشن سینگولار با نیروهای محدودی توی عملگرامون، با نیروهای محدودی در عملگرامون میتونیم نیروی خیلی زیادی رو توی اند افکتور جابجا کنیم. And this often occurs at the boundary of the workspace, fully extended, fully retracted, as we talked it in inverse kinematic. Any questions? So, in terms of reaching to the point, as you see, this giraffe is again becoming a singular configuration to reach to the highest point of interest, or getting, we come into the singular point to lift very heavy loads. In both cases, we use the desired configuration. The singular configuration is very desired and very fine with us. But usually, otherwise, in the term of the velocity, this is not the case. Now that we have found these two issues quite well, if we understand the physical properties in here now, we can find where the Jacobian becomes a singular. Now the derivation of singular point is of our interest, and this you should work on that for different examples in your assignment and your project. And by the way, the assignment are given for the next week to you, since we need to run this program quite easily afterward. Okay, if we have a 6x6 Jacobian and a square Jacobian for now, we can decouple like what we have done with the Pieper theorem. We can decouple the orientation from the velocity, from the angular, from the translational velocities. We can also decouple the Jacobian like this. Usually we have the arm and we have the wrist. We have three first joints usually to reach to the space, and then we have the wrist point, and if we have intersecting point, the wrist would have 3 zeros here, since we don't have any position. The P or the P star is equal to 0, or the S0 is equal to 0, as we derived the Jacobians in the previous sections. You see that the Jacobian wrist will be like this, with the S hat as the screw axis. So the Jacobian becomes this way, and this means that we can certainly define or decompose the determinant of a lower triangular matrix in terms of determinant of the main two parts, the Jacobian of the arm, the J11, and the Jacobian of the wrist, J22. And then we can find the singular configuration independently if the Pieper point, the Pieper theorem happens, if we have a 3 intersecting joint at the end. So in many cases, usually we call it the wrist singularity. The wrist singularity when the last 3 joints are becoming singular, or the determinant of J22 is equal to 0, and the arm singularity where the 3 first joint angles become singular, and the determinant becomes 0. And we can do that for a number of different manipulators that we have defined up to here, as we see in here. Let's talk about the wrist one first. The wrist one are similar and very usually simpler. We have 2 wrist configuration defined in our kinematic case. One of them was the 3 intersecting one, like WU-W Euler configuration, consider 3, Z3, Z4, and Z5, all of them intersecting at one point, and we would like to find the Jacobian here and the determinant of the Jacobian. We can see very simply, not by deriving the Jacobian, by considering the physical properties, that the Jacobians are the screw axis. We have 3 axes here, one here, one here, and one here. When these 3 becomes dependent to each other, or these lines becomes collinear, اگر این 3 تا بردار با هم موازی بشن یا در یک خط قرار بگیرن، این ماتریسی که از این 3 تا بردار تشکیل شده حالت سینگولار قرار خواهد گرفت. We can see that if these 3 vectors or these 3 screw axes becomes collinear, then we have singular configuration. And when this will happen, we can see very easily from here, if theta 5 is equal to 0 or 5, here it is equal to 0, and Z3 and Z5 are in the same direction. So we have the singular configuration. The determinant becomes 0 because we have dependent columns in the Jacobians. And this is very similar to fully extended or fully retracted. There we have sine of theta 2 equal to 0, that theta 2 is equal to 0 or pi. Here we have theta 5 equal to 0 to 5. Without defining the Jacobian or deriving it, we can just find the singular configuration by inspection and by the meaning of the screw axis here. The same thing can happen for another wrist configuration. Consider that now the wrists are not all intersecting at a point. We have a Z1 here, Z2, Z0 here, Z1 here, and Z2 there. I'm very sorry, this is not RISP singularity. We should call it arm singularity because we have 0, 1, 0, 2, and 0, 3. This arm singularity, in many manipulators, we have a rotating base and 2 R configuration as we see in here. We can find the determinant. We can find also from physical property when the determinant becomes 0. If you find the determinant, if you find the Jacobian of the determinant composes of 2 parts, and each of them is equal to 0, then we have a singular configuration. We can find either S3 should be equal to 0 or A2C2 plus A3C23 is equal to 0. Let's see when this happens for this elbow manipulator. You can see that, again, this should be arm. I'm very sorry about the mistyping here. S3 is equal to 0. This means that we have a fully extended arm at this point, or theta 3 is equal to 0, fully retracted arm, like what we had before. And this is the boundary of the of the workspace here. This gives us the first configuration when S3 is equal to 0, fully extended or fully retracted arm, the second part, or this part becomes to 0. This is also a very interesting point. When this becomes 0, A2C2 plus A3C23 is equal to 0, we have something like that. We have a point, we have an end effector which is on the top of the head. We have the end effector exactly at the same point at the base. We have not collinear here lines, but intersecting line that at this point, again, this relation becomes 0. And when this relation becomes 0, this means that basically we are in the singular configuration. And this is not just one point. If you rotate it, in all rotation that we have, just your hand should be on top of your head. If you rotate in any direction, just if your hand is on your top of your head, if the hand is on the top of your head, then we have in the singular configuration. We have many singular configuration here. Here there is only 2 singular configuration, but here we have many singular configuration, or a subspace of singular configuration for this case. And note that if the arm has some offset, if it has some offset between the base and the angle that we have, which usually happens in many industrial manipulator, then this never happens and this singularity will be removed. These 2 types of singularities are the most significant part of the singularity, as you see, and usually we can consider that for many other manipulators as well. Again, let's see 2 other one. Here we have another arm singularity. We call it 2RP here. Consider 1R here, 1R here, and 1P here. And again, from this inspection that we have in here, we can very simply see if the hand is on top of the head, if it is just straight, if we have no offset and this is just straight, this will comes to a singular configuration. Of course, you can find the Jacobian and find the determinant of it to find the singularity, but we can find it quite easily, as we can see in here. And finally, maybe the last but not the least example is the SCARA manipulator. We are familiar with the SCARA. SCARA has a rotating base and 2 axes that we have in here, one here, and then we have a prismatic joint in here. when this happen, again, we have the singularity for fully extended or fully retracted case. We can see that the Jacobian is like this, where a1, alpha 1, alpha 2, 2, alpha 4 is given by the sign of the joint angles from the Jacobian that we obtained earlier in this chapter, and determinant becomes 0 if alpha 1, alpha 4 minus alpha 2, alpha 3 is equal to 0. This gives the Jacobian, the determinant of the Jacobian, and this will happen when theta 2 is equal to 0 or pi. Again, the same fully retracted version that we have in here, the same thing will happen in here. Even if the scala is fully extended or fully retracted, we are at the boundary of the workspace and we are at the singular configuration in here. Of course, you can find many other examples as well. Any question up to here? Mohammad Mehdi, yes, please.
Sorry for as for example, I can see that in the singular point, it reached the boundary, but will you explain by the axes how they are related to each other now?
By the axis, you mean the collinear case of the axis. This is not very simple to see that. You know, when two columns are collinear, I'm sorry if you just turn off your microphone, because I'm opening the voice of the videos here. We have two videos, very interesting videos here. You see, the answer to your question is we should have dependent rows. This dependent rows means either there are there are two lines because there are 6 by 1. Either there are quite parallel to each other, then very simple as you see the boundary. But sometimes, as you see in this case, or in this case, maybe they are not simple parallel because we have basically larger than 3. They are somehow depending on some configuration. Usually, the point comes on top of the head. This also provides a singularity to us. It cannot be seen as parallel angles, but again, we have dependency in here. You might consider more in detail the geometry of that to see the case. But usually we have this type of configuration in many other cases. Any other questions?
Thank you.
Thank you. Okay, let me go to the last interesting part of this presentation. I will show you two videos about dexterity. We talked about singularity, the point that we are avoiding, or the نقاط تکین یا نقاط بد, non-interesting point of singularity. Let's talk something else on the other edge about dexterity. مهارت, چالاکی, چابکی. When we are talking about being very, very smart. And this comes in two examples from the nature. The first one is the cobra attack. When a snake would like to attack its prey, it comes to a very particular configuration. Note that a snake can be considered as a robot because it has a number of bones, not a 6 degree of freedom, larger degree of freedom. Let's see the attack first in here.
Of India's 4 cobras.
You saw here, as you see, look at the configuration the robot becomes, this snake becomes. Look at the head, this configuration, special configuration, and the height it comes up the floor to make the attack. And you see very, very fast speed, very, very fast speed that you cannot move away from it. To see the again the speed here, this is another snake. It is interesting that cobra is not as very, very effective killer than this small snake, as you see in here. This snake usually never leaves its prey. You look at the way it will configure itself. Look at the top version here. It is unbelievable. The speed that it can have, as you see here. Look, it uses all the actuators here to have very, very fast speed. The speed is reduced in here to see, wow, how it can happen. Does it related to anything about the Jacobian? Look at this top part again. Wow. We call an optimal posture. It has some certain posture that can be optimally devised. We would like to talk about this posture and the direction that we will find, not the way that we cannot reach to a point, not to have the enough speed, but to have the effective point and to reach to the prey or to the effect that we would like to have with the fastest possible speed. Now let's see this, the other one. Here, just look at the finger. We call the dexterity. The definition is skill in performing tasks, especially with the hands for a human. We are dexterity or tardasti or chaboki or chalaki in Persian, very quickness. And look at the hands in here, what it performs. I don't talk and just show you what it will happen. Look at the hands. Look at the fingers. You can see the trick here if you see the movie several times. Look at the fingers. Now the final touch that will show how it will work. Was it amazing? Let me just turn off and turn on again without the audio sharing, that we don't have this echoing sound here. Quickness of the hand. It was clear from this movie. If you look at the movie in detail, you know, although it is, اگرچه به نظر مثل این کارتا رو بر میزنه ولی اصلا بر نمیزنه، همه جا سر جای خودش باقی میمونه. It doesn't mix the cards. It just moves the hand so quickly that you think that it is mixing the card. Look at here again. Seems that it is mixing, but it is not mixing. They put everything on its place. My point is not the trick here. My point is the velocity of the end effector. We would like to have the velocity of the end effector. And this is one of the main real difference between human and the other biological animals or a creature on the world. Very quick with the hand. And this quickness shall be defined and related to the Jacobian. It is defined with the Jacobian. Now, let's see how we can define it. We call the quickness, consider that we have 6 degrees of freedom at least in multidimensional space. So we use a norm of a square norm of the velocity in the joint space and in the task space to define this quickness. Consider that we have a norm-bound velocity for the joint. Of course, this cobra or this the man that you showed the movie doesn't have that much very fast or unlimited velocities on the joint, but it has a configuration, it uses a configuration to have very fast velocity at the end effector. So we consider a norm-bound velocity at the joint, and we derive the velocity at the end effector. What is required for us is the velocity of the end effector. And you see that since we have the norm 2 of velocity defined here, we have a J inverse or J pseudo inverse, depending on being a 6 degree of freedom or more than that. Not Cobra, not this man, no, none of them are square matrix. They have more than 6 degree of freedom actuators, but in general case, we have pseudo-inverse here, pseudo-inverse tau, and pseudo-inverse x dot. If we multiply this together, this becomes pseudo-inverse of J transpose, pseudo-inverse of J. This is J transpose inverse. And no matter what is the number of actuator, if it is squared or not, if your Jacobian is fat, being this way, or tall, being this way, having the number of very large number of actuators, we have a fat because we have different screw axles. If we have many actuators, we have a fat or a redundant manipulator. Or we are told if we have less number of actuators, we have under-actuated system. In either case, either this way or that way, no matter which one, JJ transpose is a square matrix. And we can find this by the inverse, not a pseudo-inverse. We don't need a pseudo-inverse here. It is always a 6x6 matrix, which has an inverse, a completely inverse case. Not J, but JJ transpose. JJ transpose is something like J square, something multiple. It is a squared matrix. And we define the dexterity or manipulability ellipsoid. به فارسی ترجمه اینا خیلی سخته. دکستریتی همون تردستی یا به اصطلاح سریع بودن حرکت دسته. منیپولبیلیتی قابلیت حرکت دادن، قابلیت رسیدن به یک موقعیت. ما نمیدونم فارسیشو چی ترجمه کنیم، ولی میتونیم بگیم حالا تردستی و چالاکی یا چابکی، حالا به این ترتیب نگاه کنیم، ولی مفهوم خیلی شبیه همه. No matter how, it is a difference between dexterity and manipulability, but they are very similar, and we can define it mathematically and rigorously by the manipulability ellipsoid. And the manipulability ellipsoid is written here. So again, consider the inverse problem. If you consider this inverse problem, that the q dot is given and x dot is like that, the relation between x dot and q dot, the norm, the two norm of these, not just the simple, but the two norm of it, is JJ transpose inverse. This means that if we have a limited actuated speed, very uniform, if we have a square here in our hand, in the vector, this square might change to an ellipsoid, 6 degree of freedom ellipsoid. We can just show the 3 degree of freedom here, but we have in mind 6 degree of freedom. Either this square or this this sphere will result into a ellipse. All uniform velocities will go to very different rate of ellipse. This means that if we have a uniform velocity at the actuators, we might have non-uniform velocity at the end effector. Very, very fast velocity at the end effector, at certain direction. Which direction? You see, the cobra needs a direction that will hit a certain direction that will hit its prey. And this man was working with the card, needs very fast finger motion about the direction that it just mixed the card. And you don't see how it is. It is so fast you cannot do that. You cannot see that. This at a different direction, it might in some direction be very slow, but in some direction be very, very high speed. And this ellipsoid shows how this will move. And we can define the dexterity because of this, out of this ellipsoid. Now consider two extreme cases. One extreme case is, now we don't have the Jacobian, just the Jacobian itself. We have Jacobian transpose. As you see here, Jacobian transpose comes into the picture. Jacobian transpose we can characterize it by the eigenvectors and eigenvalues of this Jacobian matrix, by the eigenparameters. This Jacobian matrix, this JJ transpose, has 6 degrees of freedom, or 2 or 3 depending on the case. It has a number of eigenvalues. And we can find the determinant by the manipulation or multiplication of the eigenvalues. If this is 0, extreme case, if this is 0, if one of the eigenvalues is 0, we have singularity, we are dead. We cannot move there. The velocity becomes very small. If one of the lambdas here, there exists a lambda is equal to 0 for JJ transpose, we are a singular case. What happened to this ellipsoid? The ellipse will change to like a ostovane, like something like that. It is extremely large at one point and then very narrow at the other one. We have to reach to a cylinder instead of an ellipsoid with a certain direction. Which direction? What is this direction? We have an eigenvalue and an eigenvector. The eigenvalue is equal to 0. The determinant is equal to 0. And what is the direction? The eigenvalue. The eigenvector of the 0 eigenvalue gives you the direction. Which direction? You have non-reachable speed here. The ellipsoid is changed to a cylinder in VI, which VI is the eigenvector direction, and there exists no finite velocity to reach to task velocity in VI. This will become very, very large. As we saw before, the determinant will be 0, and the determinant will give you the very large velocity at the end effector. This is one extreme case. The other extreme case is the isotropy. We call it isotropy. Isotropy is better. Isotropy is the case when this ellipse remains as a sphere, doesn't get larger in one direction in the other direction. Consider all lambda i's are equal to 1. And the of the Jacobian. And Jacobian transpose is equal to I. It is not singular, not even close to singular. It is quite far from singularity. And we call that very, very interesting. We call ایزوتروپی. ایزوتروپی همگن بودن، همسان بودن، همجهت بودن توی معانی مختلف فارسی داریم. این معنیش اینه که ما اگر در همه جهت میتونیم سرعت داشته باشیم، هیچ جهتی نیست که سرعتمون رو از دست بدیم. So in this two extreme case, we have the singularity and the isotropy defined well in here. And we can examine, of course it is very difficult to show or to visualize that, but it is conceptually very easy to find that. Of course, for a 3x3 matrix, we can visualize the isotropy, this sphere and the ellipsoid here, but more than 3, of course, we cannot show it, but we can find many interesting things. And you see a cobra is so optimized to have a very, very good and very effective Jacobian transpose, let's say. Jacobian transpose shall be far from a singularity. And how far? Depending on that, we are close to isotropy, as we can see isotropy. And the problem is, you notice that Jacobian is configuration dependent. So maybe in some point we have very good Jacobian. The point where you are writing, the configuration that you are writing or painting something with your hand is very good. It is close to isotropy. We will show that. But some points are very far and very hard. When you are opening a curtain, when you are fully extending, this is another configuration for the same old hand that we have. But some places is good, we are close to isotropy. Some place is bad, we are close to singularity. And usually we are a mixture of that. And the snake will come to an optimal pose, will come from, as you see, a certain direction that it has, and it is unbelievable. If you examine that optimal case, you see that it is very, very close to optimality when you find the Jacobian from this system. Anyways, now I just end with this section and we will gain the system. We can find the norm or a measure for manipulability, which we call a manipulability measure. You know, consider this determinant, multiplication of the lambdas. The multiplication of the lambdas will provide a gain for the system. And since this is Jacobian transpose, the people who know well the linear algebra, and all of you are familiar with linear algebra, we have something in a matrix called the singular value, not eigenvalue. Singular value can be defined for any matrix, either square or non-square, in which the singular value is the square root of the eigenvalue of JJ transpose. The singular value of a matrix J is equal to the square root of the eigenvalue of JJ transpose, the same old JJ transpose as we talked before. Of course, this is true for all matrices, all A matrices. I call it especially J because the matrix of our interest is Jacobian. And we can see this singular value, since this is the square root of that, we can define a manipulability measure, a measure of how quick a system could be at a particular configuration, as the multiplication of the square root of multiplication of the lambdas, which are exactly multiplication of the singular values of the matrix J. Either you can find JJ transpose and the lambda of that, or don't go through that and just find the singular value of matrix J, singular value of matrix J. And we define a manipulability measure as the multiplication of that. This is one measure that has been defined. Multiplication of that. If the multiplication becomes 0, we are singular. One of them is 0 and we are singular configuration. Very bad configuration. If becomes 1, then all the singular values are similar to each other. We are tending to isotropy. It is a good case. And usually we are something in between, and we can define the manipulability measure as that. I will stop in here. I think we have enough discussion here. We need more time to spend on that. And I encourage you to see the movies and see the way that we are working on this issue to get well motivated to find the manipulability measure. Is there any questions? Zahra is with us and with no question. Hossein is also with us with no question. Do you have my voice? Or I'm talking about myself? My God. It seems that the movies were too interesting and you are a bit shocked about that, let me show you again this movie and then we can...
Sorry to interrupt you, but I think Zahra has raised her hand, but you can see.
Yes, I can see. Of course, I was waiting about Zahra's question. Okay, go ahead, Zahra. While everybody is watching this movie. Okay, go ahead, Zahra.
If we have a sphere, we have a better dexterity.
Again, I don't have your voice quite well.
Do you hear me now?
Yes, go ahead again.
I'm saying we have the best dexterity if the shape is closer to a sphere.
Yes, this could be considered. We cannot say what is the best. The farther we are from singularity, it is the better we are getting to optimal case. Or when we have depending on the case, usually what I can say physically, if we can get the most out of the joint speed that we can have, if we can find the most out of the actuator velocities that we can get at the end effector, this is the best case.
And it doesn't matter which direction it is when it's a sphere?
It is important. Depending, if you are isotropy, it means that in all directions you are good. Sometimes you don't need all directions. Sometimes you need a particular direction. This cobra needs all direction. Why? Because the prey could be in any direction. It can even, the prey can move away in any direction. It should hit it quite fast. But sometimes you need a particular direction. Then that particular direction would be fine.
And why in singularity we have a cylinder? It looks to me it could be a line.
It is a line in one direction, but since we have ellipsoid, we have a 6 degree of freedom. Don't consider that the 2x2 example that I gave you. In 2x2 example, it would be a line. But if you have a 6x6 general manipulator, then it would be a cylinder.
So it should have some direction that can work.
Of course, many directions that can work, but one direction cannot work. At least one. Maybe this direction is good. As you see in this example, as you see, you can consider that as a physical concept. You see, at the singular point, we are fully extended. We cannot move forward. We cannot go forward, but we can move this the other way. Mm-hmm. We can go in this direction without any problem, even maybe better, because we have lost the other direction, but we find this way. We don't say that it is good or bad, the good or bad depending on the application, but we are getting singular at one direction and maybe not singular at the other direction.
If we are losing one direction, does it mean that we are having higher speed in other direction, like if we haven't?
Usually this is the case, because you have a limited source of power or energy at the Q. When the Q's, we are transferring it to the X by JJ transpose. If in one direction we are losing, the amount of energy will distribute in the other direction. And this might be good even. In some particular case, you don't need one particular direction. You can go through that singularity, and as you see in here, we are losing something here and gaining something else. We can move in some direction. We can have a very heavy load in this direction. Of course, very limited motion, but very larger force motion that we can have.
Okay, thank you so much.
You're welcome. Hussein, do you have any question? Well, just quick, because some other question we have in here. Go ahead. Hussein?
Good morning.
Good morning.
Yes. My question is somehow technical. Okay. When we examine, as we saw in your slide, in the slides, as we examine the Jacobian matrices, we are examining in order to determine the singularity, we aim to determine the eigenvalues. Okay, and it's related to the sines or cosines of the angles. In the example in slide 49, as an example, we saw that theta dot is 1 over L1, L2 sine theta 2. At theta 2 equal 0, there is a singularity. Okay. Say, for example, we have theta 2 is 1 degree or 2 degrees. Theta 1 dot theta sine 2 is too high, is too small. Yeah. Then theta 1 dot is high.
Too high.
Is too high. So we have limitation to the used actuator. Okay. Mm-hmm. Is this limitation will reconfigure the workspace of our robot?
Not about the workspace. We talk about the workspace without any limitations, Since, as you saw, when we were talking about the workspace, can you just turn off you mute your microphone? We have the echo here. When we'd like to find the workspace, we might have some limitation on thetas, but we might have the limitation on theta dot and theta double dot, even the acceleration limitation we have. We don't consider that in the workspace, but we consider that in the next step, in the manipulability cases or measures, or in the we call it manipulable workspace, something like that, or feasible workspace instead of reachable workspace. Reachable workspace doesn't give this limitation, bring this limitation into the picture, but these are important. Then this is not just a singular point which is not reachable. Of course, singular point, we are dead. We cannot reach with any actuator. But even we become near singular, this is also not good. So we should avoid being even near singular because of the same main reason that you say. We don't have infinite velocity actuator with us. We have very, very limited velocities in the actuators.
Thank you. We have a new limitation.
Yes.
The constraints or the limitation about taking in consideration the speed will restrict us. Oh, okay.
Yeah.
Thank you.
We will talk about that. Again, we have some acceleration problem in the next chapter. We compete some other constraints there.
Thank you.
Mohammad Mehdi, you had a question, but it seems that your question is disappeared. If you have still your question, please contribute.
Thank you. In the shape, we had the sphere and the ellipsoid. What does the distance shows? When it is smaller, it is more dexter, or it doesn't show something like that?
You cannot say one-to-one, say. When we call a dexterity, we should have a measure. The measure is defined here, manipulability measure. I will talk about that next session, because it is too much of information given here. Of course, if mu is farther from zero, the farther from zero it is more manipulable. But it might be not one, it could be even more than one, depending on the gain or the singular value that we can get to here. If there are normalized, then the highest value is equal to 1, which we call the isotropy. So in terms of the ellipsoid, you can see, you can visualize. If we have a sphere, it means that we can move in all the direction, in any direction that we would like to move. That means that it is a very good configuration. We call it isotropy configuration. But note that optimal or being good or bad is a qualitative issue. When you would like to make it quantitative, just one measure is not enough. You shouldn't look only on one direction. You should look on different directions to have a qualitative value being defined. And this is what is done in nature. The biomimic robotic comes from here. We go through the nature from different aspects. One of the aspects is Jacobian. Some other aspect we haven't talked about yet is the actuator, the limitation. Why I talk about the snake is a manipulator, a special manipulator. If you look at a robotic case, with many number of degrees of freedom. You have 127 joints in a snake. And for the attack, it doesn't use all the joints. It might use the ending joints in here. As you see in here, let me just again show here. If we go in here, maybe sometimes here, look, all these are some joints in here. The most significant part are near to the neck. Look at the configuration. And the configuration is like something like square. And this is not just about the speed, it has some acceleration limitation here. The muscles of the snake are also limited to this case. And if you look at that, this special S shape that it configures is very good for its motion. And I like it very much, and I also recommend you to look at the nature and look at the secrets that are behind the designs that are given in the nature to find optimal design. In short, optimality or being good or bad is not very, very simply defined by human. It is not possible to define that. We look at the optimality only from one direction.
Thank you.
Thank you very much for everybody and for the contribution you had, and try to read the material here for the next session, because we would like to go to some more depth mathematical calculation in the next session. And don't worry to provide, don't forget to provide the solution to the assignment and project just by time. Everybody, thank you very much and good day.